All right, guys, so I wanted to talk to you about how to calculate between grams and moles, grams and particles, and moles and particles. You've done this before with elements, but now we're going to do it with compounds. So, first thing I want to tell you is there are molecules that are diatomic. And diatomic just means that these elements are never going to be by themselves. If they're in a compound, they don't have to be diatomic, but they're going to either be in a compound or when they're by themselves, they're going to be with another one of themselves. So I have a saying I use, and it's called Brinkelhoff. And this is the elements that are diatomic. So bromine is always going to just be Br2 if it's by itself. Same with iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. If you look at a periodic table, a rough periodic table, you can see they do form, if we ignore the noble gases, they form like a 7. We can look on the periodic table. They're all there except for also hydrogen. So here's an example problem, and if you guys have your pink mole map, you can use that to help, where we can calculate, we know how to use Avogadro's number here between moles and the number of atoms. We know how to go between moles and mass by using molar mass. So the only difference is now we know how to calculate molar mass of a compound and not just an element. So for this question, they want to know the mass in grams of 2.5 moles of oxygen. So 2.50 moles of oxygen. So you always want to start with the number you're given over 1. I recommend that you write down what it is. Here's where I'm kind of getting messy, but that's where I have that 2 because this is a diatomic molecule and this really matters in order to get the answer correct. So I'm starting here and I want to go to mass in grams. So I would use the periodic table, this one, so I know I have 2 oxygens. Molar mass is 16. So my molar mass of oxygen is 32 grams per mole. And if you remember, we can take that 32 grams and think of it as that's an equality. And then we can write it as 1 mole over 32 grams or 32 over 1 mole. So because we're trying to cancel the mole here, we're going to use this one. So I'll put my 32 grams of O2 here in 1 mole of oxygen. These cancel, and then I end up with an answer of 80.0 grams. So sig figs, I'm not interested in this. These have infinite sig figs, they're not measurements. I'm interested in this number here, 3 sigs, so I end with 3. Okay, so I wanted to show you some other types of mole conversions. So here's a question, ibuprofen, which is, Advil. Ibuprofen's the generic. It's a painkiller, pain reliever, and it has a molar mass of 206.31 grams per mole. So we've already calculated it for you. But, if you were to, it would be 13 times 12.01. 18 times 1.008 and 2 times 16, and I would add those up. But I'm just going to write this molar mass of, and then we'll say it's IB. That's how many grams are in 1 mole of IB or ibuprofen. So in this question, I have a 33 gram bottle. So I'm going to, start with my beginning number over 1. And this is of the ibuprofen. And then I know I'm going to use molar mass because I'm trying to figure out how many moles of this ibuprofen I have in the bottle. So I'm going to use this up here. So I know there's 206.31 grams of, let's use the real thing here just for fun, in 1 mole of ibuprofen. So when I calculate this, you can see that my grams of ibuprofen cancel. I end up with mole. I take 33 times 1 divided by 206.31. I have 2 sigs here, so I'm going to want to have 2. So my answer is 0.16 moles of ibuprofen in that bottle. Now they want to know how many molecules this is. So I could start with my grams again. And I can show you, I think I have the mole map down here, that, you know, I could start with grams and go to molecules, and you know how I can't go directly there. So I'd have to go from gram to mole like I just did, and then mole to atoms. So because I already did the mole to atom, grams to moles, I'm going to start with my answer here. So 0.16 moles of ibuprofen, and I always write that over 1. And then I'm going to use Avogadro's number. Remember, that's how many atoms, in this case molecules, because it's a compound of ibuprofen, are in 1 mole of ibuprofen. So then you can see that my moles cancel. I end up with molecule. On my calculator, I'm going to take 0.16 times 6.022, and then I would use your EE and then just put the 23 in. When you do that, you're going to get 2 sigs, 9.6, 10 to the 22nd molecules of C13H18O2. So last problem, we want to know the total mass in grams of just carbon in that 33 gram bottle. So this one's a little different, and I could start with the 33 grams and convert it to mole, but again, I did that up here. So I'm just going to start with my moles of ibuprofen, and I'm going to realize that I'm only talking about carbon now. So in this compound, I can interpret these subscripts as moles. So for every 1 mole of ibuprofen, there's 13 moles of carbon, 18 moles of hydrogen, and 2 moles of oxygen. So in this case, I'm going to convert to moles of carbon. So I'm using that subscript for every 1 mole of the whole molecule ibuprofen. So at this point, I'm in moles of just the carbon that are in the bottle of ibuprofen. And then lastly, if I want to know grams, now I know that carbon has a molar mass of 12.01. I can look that up on my periodic table. So now I'm going to take 0.16 times 13 divided by 1 times 12.01 divided by 1. I know you don't have to do the divide by ones, but and then you end up with 2 sigs because we started with 2, so 25 grams of carbon. So in that bottle of 33 grams, 25 grams of it is carbon. The rest of it's going to be hydrogen and oxygen.